Hi everybody. Today we're going to look into a technology on how to measure the chemical content of an alloy. If we look back in old days, chemical composition was measured by a chemist, water chemistry, dissolving, evaporating, distillating, or producing sulfates, segregating, centrifugal drying, and measuring. It was a very long way of doing it. It took typically 2 to 4 hours. And if you make a melt of steel, and you want to measure the chemical content of that, the carbon content, then you cannot wait for 4 hours to make your steel. So therefore, a sample was taken and it was sent to the lab for the wet chemistry analysis. But another sample was taken, and at that time, when we look back, before 1936, there were pretty skilled people who could visually see the chemical content of a steel by making sparks. And I have been in the vault. Check this out. This is a test or a reference set. Here you can see different probes, and you can see the spark, how it is expected to be as function of chemical content. And if we look at the first down here, the main difference is the carbon content. So if you can see the difference between that and that one, then you could tell if you had 0.3 or 0.5% carbon in it. But to be able to do that, people had to be extremely skilled. It was a process that took years to learn, and still it was very inaccurate. And therefore, steel at that time was not made the way it is today. Today, it is a perfectly balanced in the carbon content, in the manganese, in the silicon, and reduced in sulfur, reduced in manganese, in phosphorus. It is so well controlled because today you can measure the chemical content. This episode is about that technology. So hang on, because I have invited specialists from the company LECO to tell about the way to measure the chemical content. We start looking at the first generation carbon-sulfur LECO tester. Then we look into what I call next generation, the nitrogen, hydrogen, oxygen methods. And then finally, we look at glow discharge OES. That is pretty amazing what is possible. Just compared to what I knew 20 years ago, I was blown away. So I would encourage you to take a look at this episode and see it all the way through, because Michael here, he's pretty good at it. Enjoy it with Michael and LECO. Hey, and on the way, there's also a demonstration in the lab. So hang on and see how it's done in real life. It's pretty cool. Enjoy it. Hi, Michael. Welcome to the podcast Everyday Metallurgy.
Hi, Peter. Nice to meet you.
Yeah, thank you. And thank you for joining in. You are from the company LECO. And when I grew up as a metallurgist, I thought that was the method and not the name of the machine or the company, because it was so grown in that I will make a LECO test. But in fact, thinking of it, I do not really understand how it is measuring. So that was why I would like to learn a little about how does the machine really work? What is happening inside it? And we are going to talk about the traditional sulfur carbon, but we're also going to look into next generation machines, oxygen, nitrogen, hydrogen, because hydrogen is becoming more and more popular. People are talking about hydrogen embrittlement and can you measure that and so on. And then we are going to talk about glow discharge OES at the end. But Michael, will you give a short introduction to yourself,
Of course.
beginning with not letting me talk all the time?
That's fine, Peter. Yeah, my name is Michael Jakob. I'm working for LECO since 32 years now. I'm European field product manager for a part of our products, especially the products you mentioned, the old so-called LECO products, which are, of course, is a carbon-sulfur analyzer. And this analysis is really called in many laboratories LECO analysis, which is for us good. If you have a nice name on the other side, of course, you have to care for that you keep the customers happy. That can be challenging sometimes. But we're quite happy that we have this name in that field. And LECO, yes, of course, we have carbon-sulfur analysis, we have oxygen, nitrogen, hydrogen analysis in steel, in metals, in ceramics, in high-tech materials, in alloys. Yes, we do. And additionally, you mentioned it, we also have this glow discharge spectrometry.
Yeah. So should we start digging into the old boy in the glass, the carbon-sulfur analysis?
If you like, I can show you some 5 to 10 slides about that.
Yes.
Where we come from. So if that is okay for you, I can definitely start sharing my screen. Give me a second. Hope that works. So you should see my screen now.
Yes. It runs perfect.
That is okay. Okay. Again, you see this where we come from. You see this machine here on the left side, which really was the first carbon analyzer built in 1936 by the founders of LECO. Of course, meanwhile, nearly 90 years passed by, and it's not looking like this anymore. But this is where it all started with. So, LECO is still an American company. It's still family-owned. We have around about 1,500 people around the globe, and of course, the instrument is not looking like this anymore. We're doing much more things, as you see here on the slides. But the most important thing, we still do carbon, hydrogen, nitrogen, sulfur, oxygen analysis. And the modern carbon-sulfur analyzers are looking like this. You see, we still have a crucible where the samples is burned, and we will have a few slides on that soon. That is the overall shape of the instrument. We have in the moment 2 analyzers, one standard analyzer, the CS744, and some advanced one with a higher sensitivity and some more features, CS844. But whatever you do, you put your sample in a crucible. It's a ceramic crucible. And what you do, you bring your sample, and we talk about metallography, so metallurgy in your podcast. So metallurgy means it will be metal samples, but of course also other samples like ceramics or even soil or things like that could be analyzed. So what you do, we bring the sample in a high frequency furnace. This is what you see on the left side here, where the crucible is directly in an inductive coil. We're adding sometimes or most times an accelerator to enhance the coupling efficiency of the high frequency field. And then we have a simple combustion process, and we just burn the sample to CO2, SO2. Of course, you form maybe also some moisture.
Yeah.
And those gases we create here are later on simply analyzed by 2 or 4 infrared cells. I just have the gas flow schematics of this CS744 here. So, but the 844 is more or less the same. We just have more and more sensitive SO2 and CO2 cells. So very short. We have oxygen from the bottle. We have the high frequency furnace. We have some dust filter, some flow scrubber, and then we have 1 and 2 infrared cells for the IR detection of SO2 and CO2 directly from the sample. So the overall process is around about 60 seconds.
I have 2 questions now. The first is, what temperature do you reach in the crucible?
Yeah, that is a little bit dependent on which materials you have, but if you make an estimation, you can say we easily reach temperatures of near to 2000 degrees C. That melts the sample in few seconds.
Yeah.
Yeah.
And then the other is, when you reach these temperatures, you're not producing CO2. You make a lot of carbon monoxide.
Yeah, keep in mind. Theoretical, if you look to the Boudoir equation, yes, but practical, more or less not really, because we're running a huge oxygen surplus in the system. We have really a lot of oxygen. It's running under pure oxygen.
Okay.
But the question is good. If we form for some samples some carbon monoxide, we can't detect it with a CO2 detector. This is why we have on the right side here this catalyst furnace, which is oxidizing CO to CO2, exactly to prevent that what you mentioned.
Yeah. And then the Mollite crucible, as I remember, the melting point of that is around 1900. So are there materials that you cannot melt and measure?
No, I mean, keep in mind, again, I don't know exactly the ceramic at the moment we really have there, but that's never a problem. Of course, if you would run this crucible for, I don't know, many minutes, there would be a threat that you melt the crucible and that you burn a hole in the crucible. But under normal analysis times of 60 seconds, or nearly 60 seconds, it depends, this is not happening.
No. So you can measure refractory materials even though they have melting points far above 2000.
Yes, definitely. Keep in mind we're adding some accelerator. The accelerator is tungsten, or it's a tungsten tin mixture, or maybe also some high purity iron powder. There are many possibilities. They will form a sort of eutecticum
to lower the melting point.
And it will also lower, the main thing is the coupling, but it will also lower the melting point. So we never found any metal that is not really melting in this hot molten liquid metal bath. This is normally analytically not a problem.
Perfect. Thank you. I have no more questions right now.
Okay, now just let me show you the last few slides.
Yes.
Of course, the heart of the system is infrared cell. What you see there, we're producing them on ourselves. It's a self-heated design without any moving parts, and this gives you just some benefits, especially of very low drift of the system and high reliability, because there are no moving parts in the system anymore. Okay, let's just say we have also auto cleaner availabilities. We have auto loaders available for the system. You will see that in the laboratory in a few minutes. I will not talk about software features, just a few things what we can do. And this, coming back to your question from before, we can do, of course, all these metals that you see normally, from copper, aluminum, refractory metals, of course, the whole steel samples from low alloy, high alloy steel, but also things like glass or ceramics or limestone, catalyst material. There are really a lot of possibilities.
Yeah.
Okay, I don't want to go really now to all the details. That would lead us, I think, to two specific questions.
Yeah, everything is possible. Because to melt it, if you add in iron, then you also can create the inductive field, because when you just do it with sand in an induction,
yes,
nothing
you're
happens.
absolutely right. If I have non-conductive samples, I have to add something that couples, and in that case, we normally take iron chips plus accelerator in most cases. So you're absolutely right, because non-conductive. So if you put a non-conductive sample, let's say a piece of ceramic in the crucible, it will stay cold. It will not even be one degree C higher than before after analysis.
Yeah. And Michael, you promised that you would give a demonstration on how it works, and I can see the lab is open now.
The lab is still open, even if we have to. And I will spotlight for everyone to the laboratory. You should see it on a bigger screen now. I hope that works.
Yes, it looks fine.
And then let's see if Sasha is there.
Hello, yeah, I'm here.
Okay, hi, Sasha. Good morning, good evening.
Morning, hello.
It's afternoon.
Okay. So I would just run 2 standard samples, just normal standard LECO samples, maybe just to showing just a steer pin. Okay. So then we log in the sample. So you have here the choice between standard, sample, drift, and blanks. We are just using now the sample. Then we type in the steer pin, just the name for us. Okay. Then make sure we have the right location. So we're starting on A2. So these are the crucibles.
Yeah.
So John just place it. Oh, I take a new one. So we Terra. So just for showing, this is just a steer pin. 1 gram. Normally they are 1 gram.
Yeah.
But we also liquid also standard with half of a gram. But normally the normal mass for steel is 1 gram. Okay. Then we can transfer directly the weight to the balance. Then we place it on the right position. Take another one. Okay. So and then we adding accelerator, as Michael told before. In this case, we are using LECO cell 2. First, we
this is just
what's in an accelerator?
Mainly things like there are many different accelerators, but in that case, we take tungsten or a tungsten tin mixture. You can also use some. So if you only do carbon, you can also use copper. But this is due to the effect of the coupling. It enhances the coupling and gives you a better current in the sample. So the high frequency field is applied.
So the instrument is ready to analyze. If something, for example, you have problem with the leak or something else, the instrument would tell you, oh, not ready to analyze. So you have to check it and you cannot start it. But now everything is fine. The instrument is set up and we're just pushing the start button.
Yeah. And now you see the auto sampler running. It grabs the first crucible. And you see the first analysis takes you some 10 seconds longer than all others because it has to check if there's a crucible from the last sample, from the last run in the system. Yeah. It has to take the first crucible and so on. The next one will be much quicker because it will take the next crucible and put them in the holding position. Then it's just, you will see it in a few seconds. Yeah. So
how did you measure carbon before 1936, before this invention?
They did that. Yeah, that's a good question. I'm also not sure. They did that with some wet chemistry method, taking you half an hour or even longer.
Yeah.
And keep in mind, why is it important to measure it quickly? Because your molten metal is anywhere in the ladle or in the furnace or anywhere in the steel plant waiting for being either alloyed or being casted anywhere.
Now it's glowing.
Yep, now it's glowing.
Yeah.
Yeah, you see that it's starting burning, and you see the peak.
Whoa.
The peak.
And now the peak is coming.
Yeah, it's glowing a lot.
Yeah, and the sample is burning. So maybe I can grab the crucible.
Yeah, and you see the.
And the lines you can see on the graph, they represent
the blue
carbon
lines
and sulfur.
The blue line is the carbon and the sulfur peak. Yeah, the red line is just the current running in the system. It's not necessary to show. Yeah, and if you are quick, Sasha, and you're quicker than the auto sample, then you can cut.
I will try. I take it here. Put it up anyway.
Yeah.
Flap.
There it is.
So as you see, completely molten.
And you see the sample is completely molten, and the crucible is still in shape. So of course, if you would have taken the crucible for many minutes inside, it could melt. But this is really not a problem. Yeah, and that's it.
But the cheating, adding these actuators, reducing the melting point. I didn't remember that.
Yeah, I mean, that's not only melting point, it's especially for the coupling. But yeah, you're right. Okay, so that's it more or less. We can show you with the machine.
Yeah.
We can
open it. We can open it.
Yeah, you can, Sasha. I don't think it's necessary.
Okay.
But it gives some insight in how it has changed the steel production in a steel plant. Because if you go back in time and say it took at least half an hour to make this kind of measurement, then controlling the chemical composition was extremely difficult.
Yes, I mean, I'm no expert for his historical steel plants before 1930, but yes, of course, you're right.
Yeah, because today you can run an entire batch within an hour. So you can make 60, 100 tons in an hour, adjusting chemical composition and pouring it. So things are really going fast today.
Absolutely.
Thanks to this.
So we are done. So analysis is done. Yep.
Yeah, and what is the result?
So the results when we making an overlay. So carbon 0.05 and sulfur 0.0017.
Aha.
So the average, of both.
It shows you also the average and the complete statistics and so on.
Yeah.
Okay. Just as a quick overview. Sasha, thank you very much. I think.
Great demonstration.
Maybe you
can just showing how easy it is to change the furnace.
Sasha, I don't think we have the time to do that.
Okay. It's fast.
Maybe you can just for 1 minute.
Yeah.
Go around the corner and show the ONH H36. Just that we see the oxygen and nitrogen analyzer.
No problem. So it looks a bit. There was work today on the ONH, so.
Well, come on, we have nothing to.
No problem
to hide. Oh, that's a good view. Yeah.
Wait, so go a bit back.
That's okay. That's okay.
Yeah.
So we prepared some samples for tomorrow already. This is what the boxes on the right side. But just to show you the instrument, it will be of course a little bit different, because we're working, and I will tell you this in a few seconds. We're working with a graphite crucible in that case, and not with a ceramic crucible, because we want to analyze oxygen, nitrogen, and hydrogen in the instrument. So just to show you live the instrument is, I think it's better than on a PowerPoint presentation.
Yeah.
Okay, Sasha, thank you very much for that.
You're welcome.
Yeah, wonderful. Thank you.
You're welcome. So,
I think I'll stop the spotlighting, and then it should be back on a normal way. Okay, thank you very much, Sasha. Okay, Peter. Though this was a quick tour through our lab. Yeah. I mean, we could go on and talk a little bit about oxygen, nitrogen, hydrogen, if you like.
I would like to do that. I would like to learn a little more about why it is interesting to measure nitrogen, oxygen, and hydrogen. I have some point of that myself. We are making stainless steel, and we are now also making duplex stainless steel. That means that we are introducing nitrogen in the material, and the nitrogen has to be quite accurately to have the duplex structure, because nitrogen is a nickel or an austenitic stabilizer about 30 times stronger than nickel. So therefore, accuracy of hitting the right amount of nitrogen is quite important.
Yes.
Hydrogen, slightly talked about, the new era coming now with the hydrogen in pipes and in steel, and the risk of hydrogen embrittlement and a lot of accidents that could happen if you have it inside the steel. But what about oxygen? Why is that interesting to measure?
Well, to be honest, that depends on the type of steel you have. Nitrogen in high alloy steel, you talked about this full duplex steels. It's a sort of alloying material. But in many cases, it's just a disturbing material. It's just something that is bad for the behavior of the sample, like oxygen and especially hydrogen. I mean, hydrogen always is a contaminant. It's nearly never, nobody wants to have hydrogen in the system. In steel, also in other alloys, by the way, also in aluminum or copper. That's always bad. So we analyze it for quality control, but also for control of which is also quality control of the composition. If we talk about high alloy steel, where nitrogen is in the 0.5% range or up to the 0.3% range, then we analyze that with a machine, and that can be done with a very high accuracy and a very high precision.
But how does it work? It's not the same an IR analyzer, is it?
I mean, it is IR. I'm not sure. I'm still sharing my screen. I think I do.
Yes.
So if we talk about, I'll just show you a few slides about that, about oxygen, nitrogen, hydrogen. It's one thing. First of all, it depends what you want to do, but what LECO does with the ONH 836, that instrument is available as oxygen, nitrogen, and hydrogen simultaneously from one sample. That makes life easier because you don't have to run it twice. There's also an ON 736. That one has only oxygen and nitrogen. But oxygen, nitrogen, hydrogen 836 is doing that simultaneously. This is the instrument you saw on the slides on the presentation from Sasha in our laboratory.
Yeah.
And the machine is running with graphite crucibles. You saw all of that. There are different type of crucibles, but generally we use standard crucible, and there are a few more, like high temperature crucible, which gives you some higher temperature because it has a little bit different shape.
Mhm.
That's available. Yeah. The mechanics, and now coming back to your question, is a little bit different. What's happening? The sample, the steel pin, after the baking of the crucible, is falling just by gravity. There's a sample drop mechanism falling into the crucible. And nitrogen and hydrogen is really released as elemental N2H2. CO2, the oxygen is released as mainly carbon monoxide. In most cases, there's carbon monoxide, just by reaction from the oxygen of the sample with the carbon from the crucible, more or less. And what you do is, looks a little bit complicated here, but it's quite easy to understand. We have a carrier gas. In that case, we can use helium or argon. We have this electrode furnace where we can heat up the crucible up to temperatures of up to 3000 degrees C. It's a high temperature crucible.
Yeah.
Maybe not needed for steel, but for some other materials like ceramics or refractory metals that could be needed. And from there, we go over a sort of flow controller, and then we go over, I'll come back to those two cells at the beginning soon, over a catalyst furnace forming CO to CO2. Then we detect CO2 as with an infrared cell, the same infrared cell you saw before on the carbon-sulfur analyzer, the same type of infrared cell.
Yeah.
Keep in mind, this catalyst furnace also transfers hydrogen to water. Means we detect water as the water also with another infrared cell. So we have oxygen and hydrogen. Unfortunately, there is no IR cell for nitrogen, so we have to detect it with a thermal conductivity cell, the TCD detector. And before we run anything on the TCD detector, we have to remove all other gases that could influence the thermal conductivity. But we have to remove that. And this is done by a chemical, we call it LECO, but it's more or less sodium hydroxide on a sort of clay carrier. And that remove means after that, we just have carrier gas and nitrogen in the system, and we detect this with the thermal conductivity cell. Altogether, it takes you around about 1 to 2 minutes, including the sample outgas, the crucible outgas.
Do you add an additive, an accelerator here as well?
For steel samples, normally not. For some alloys, we add some, I wouldn't call it accelerator, some sort of flux. That can be nickel, that can be tin. But this is really dependent on what material you use, and that should be fine.
Yeah. And here the material you add, is it less than 1 gram now?
Yes, it depends. So, for example, if you run titanium, we add some 1 gram of nickel accelerator, or call it accelerator. For others, we take some some tin pellets as a flux reagent. So it's difficult to say because there are many possibilities.
And the sample, is that prepared by drilling material out of your steel or your test bar?
That's a good question, because as I mentioned before, we have to using sample of 1 gram, but the 1 gram from a steel block, it's not so easy to take. So you have to use any device, to get that. But there are many possibilities. There are special sampler available that is giving you already a nearly ready prepared sample for nitrogen, for oxygen. There are special sampling machines that can do that automatically.
Okay. Because I could imagine that if you drill or if you cut it with a grinder, you introduce oxides.
Absolutely.
And then you disturb your measurement a lot.
Absolutely true. That's really a problem. If you do oxygen. For nitrogen and hydrogen, normally this is not the case, but for oxygen, yes. So you have to really get a clean surface, or remove the surface anyhow. It can be very simple by preventing the surface from being created when you take some special oxygen sample, or you have to remove it mechanically by a lathe or by a grinding or filing or whatever.
Yeah. So you have to prepare it cold to avoid oxidation.
Yeah. If the sample is glowing hot, you will form some oxide layer automatically. Yes.
Yeah.
But again, believe me, it's that's not a big issue. We use that since many years.
Yeah.
The cells itself, it's the same. You saw before. It's a it's an infrared cell, same type of cell. Of course, thermal conductivity cell is looking a little bit different. I will not go into smallest details now for thermal conductivity cell. The big advantage of the LECO cell is that you can also use argon as carrier gas. Because in former years the instruments were just running with helium, but due to some issues with helium shortages and the helium price went up for, I would estimate, 3 to 4 times in the last few years.
Yeah.
That it's still, I mean, we still not use too much helium, so it's maybe not a big price issue, depending on where you buy it. But sometimes you also have some availability problems in some countries. So more and more people try to go away from helium and try to use argon as carrier gas, which is always available because it's around about 1% in the air you breathe. So that is also working fine to use the instrument with argon as carrier gas.
Yeah. And how can you be sure that all the gases are they evaporating or what do you call it?
How can you? I mean, that's a question. Like, how can you be sure that you're measuring the correct result? No. Well, we have a quite long knowledge base, and we know that at certain, you can check that with standard materials. Of course, there are hundreds of standard materials available for oxygen, nitrogen, little less for hydrogen, but also there. Available in several materials where you really can check if you have 100% recovery of your sample, because you see that.
So you calibrate it. Against other standards.
All the measurements we do is it's a relative measurement system. Means it has to be calibrated. We compare electronic counts, let's call it simple counts, with certain amount of microgram or milligram nitrogen, oxygen, carbon, whatever. And that's a sort of calibration, yes.
And are people also making round robin tests?
Just this morning we did one here.
Okay, so you also participate in a round robin?
Yeah, we do. We did it for a company, a well-known CRM company of Sweden. You could imagine who that is. We participate in round robin tests for creating CRM materials. But the LECO itself, we are accredited after ISO 17034 and 17025. So we are allowed to create our own CRM grade standard materials in our main laboratory in St. Joseph, Michigan.
Michael, you left a cliffhanger because you said when you showed the diagram of it, there were 2 IR sample before really measuring.
Yes,
and you would come back to that. And I am.
You're right.
I'm,
I forgot.
I'm curious.
You mean that one here? This one here?
Yeah, the upper ones. Yep,
Yeah,
exactly.
It is. Yeah. For some cases, for some materials, high oxygen containing materials like oxides or some other cases, you could create CO and CO2 at the beginning. And to measure that absolutely correctly, we have in the high range, they call it high range, we have some CO2 and CO infrared cells, so one of each case, before this catalyst furnace to measure it directly from the sample, which is the best way to do, and get the correct results also for very high oxygen concentrations like oxides.
Yeah,
molybdenum oxide, zircon oxide, iron oxide, whatever you might have.
Yeah. So if you want to test your iron ore, this could be the method.
That could be done definitely with a LECO machine, because we have the special ability to use those high range, this high range. Yeah. Okay.
Yeah. Perfect. Should we jump on board on the glow discharge machine?
I think we should, because I don't want to stay here. Okay. So what we can do here with glow discharge is something LECO also offers. We do that since many years. There was older GDS systems and newer GDS systems, and I really try to keep it simple, because I could talk a lot of glow discharge technology, but I try to explain it quite simple. A GDS is, first of all, it's an emission spectrometer, like a spark emission spectrometer or an ICP OES, so it's an emission spectrometer. The difference is the where you build your plasma. And the plasma of a glow discharge is a plasma that comes from a sort of sputtering process. We have a thing called anode. It's a small copper tube. You see that here. It's a 4 millimeter diameter. There are also 2 millimeter, but let's keep it as a 4 millimeter.
Yeah.
And this is called anode. And the sample itself, you put that on this anode, it's the cathode. That's the metal sample. We apply a small vacuum, so your cathode is sucked to the anode. In this, then we apply some, let's keep it with a direct current plasma at the beginning. So we apply a voltage of 1000 volts around about that. And the remaining argon atoms are ionized, accelerated to the cathode. It smashes out atoms of the cathode. They are sucked into that anode, and in this anode, there's a special area where it releases, where those excitated atoms releasing light, and the light we detect with a special spectrometer. So that gives us, well, that's how the anode is looking like. There are two anodes. We have a direct current and a combined DC RF lamp. I will have a few words later about that. And you finally add in a spectrometer. LECO is using a classical Parcher-Rungen setup, where we have the sample. At the cathode, we create the light. The light is going to the grating and then split it up into your wavelengths by the gratings.
Yeah.
We have a GDS 950 with some higher resolution, a GDS 900 with some lower resolution, but these are technical details. We also have an extension spectrometer, by the way, to extend the wavelength range from 120 nanometers to 850. Now comes the clue of the system itself, why it's really interesting to run a glow discharge application. So first of all, we can do, of course, bulk elemental analysis. Means you have your sample. That's the sample. This is the sort of cross cut. So what we can do, we can go on with a quite high energy to remove the surface. This is this white thing. And then we open the shutters and analyze some 10-15 seconds the material under the surface, and that gives you a the concentrations of theoretically nearly all elements of the periodical system, where you find a calibration. Of course, that's a thing, and you just get a bulk value like carbon 2.5%, manganese 0.6, what you see here, or phosphorus 0.0 something, whatever. This can be done by a glow discharge, which has a few advantages, but can also do them with a spark spectrometer or anything else. What is unique is the feature of the compositional depth profiling, and this is very simple. We just start at the surface, have no pre-burn, and analyze everything that comes. Means we're analyzing layer for layer for layer for layer for layer for layer. We have a resolution in the nanometer range, and in that case, you see you have a three. Maybe you have some steel, you have some, for example, you have some zinc coating and some paint or whatever. Then
case hardening.
You would see your layers of element 1, element 2, and the iron itself. Of course, here you just see 3 elements, but theoretically you see the whole periodic system with higher or smaller concentrations. And this, of course, is a perfect thing for research. Again, we can do all elements, all matrices, metals in bulk elemental analysis, but we can also do a lot of things, what you see here, like compositional depth profiling. It can be the simplest way, just you have a coachwork of a car and have some paint, and then the zinc, the anti-corrosive zinc layer, and then the steel. But it can be also very weird things with PVD, CVD, aluminum cladding, galvanizing, up to samples where you have some semiconductors or photocells or whatever.
How long time does it take to make such a depth analysis?
This is like radio. Everyone says it depends, but in that case, a normal bulk analysis is done normally below 1 minute. Depth profiling can be from 1 minute up to some 10 minutes. It really depends how deep you want to go. We end normally at 100 microns, maybe a little bit more, which is normally enough for all technical coatings. But that is what you do. And the big advantage compared to other surface analysis technologies like Auger or XPS or SIMS technologies, and keep in mind this is a logarithmic scale, we can really go up to 100 microns and below. All others are anyhow limited to some 5 to 10 micrometers. And also the area, we're talking about production control or analysis, the area is of course 4 millimeter diameter in the standard equipment. We can also have a 2 millimeter anode, but let's stay at 4 millimeter. And others like Auger, you have a few nanometers surface you're really analyzing. So that's a big difference.
And in this one, are you able to measure carbon, sulfur, oxygen, nitrogen, hydrogen?
Yes, theoretically, yes. Well, hydrogen, if you have the concentration is high enough, yes. But yes, we can analyze all elements of the periodic system. Also nitrogen, oxygen layers. I have an example for that. So, I mean, just if you take a very simple thing, galvanized steel, you see steel, the green that's the surface here on the left side. Then we go some 7-8 micrometer in the material, and you see you have what is that, 3 point something micrometer layer of zinc, and then the steel comes, the iron goes up, and here you have your interface. That's for fun. I have hundreds of such things. Just one thing that happens is quite interesting. This is a white car. And you see that's the surface. That's a cross section by metallurgy. Then you see your steel, you see your paint, and you see some zinc layer and some interlayer. And what you finally get is something like this. You see, at the beginning, from the surface, you see some oxygen, you see some titanium, of course, you see some carbon of the paint, which is a sort of, I wouldn't call it plastic, but anyhow, it has carbon. But you see titanium oxide.
The white color.
Yeah, the white color.
Yeah.
Then you have your wrong direction. Your zinc layer. And then after 50 microns or 60 microns, it's difficult to see here from my screen. Then you go into the steel. That is something you can do.
Yeah.
Sometimes the question comes how you control that. Well, the LECO machine, and now it goes really into detail, are a sputter rate corrected, so we calculating that more or less. But you can, of course, check that with, there are some standards available, like this Cocour standard, which has 6.4 microns interlayer between zinc and iron. And of course, if you see, we match that quite good with 6.42 plus minus RSC 1%. This is just an example.
Yeah.
And final example that also answers some, this is a hard disk on a 1 terabyte hard disk. Of course, on a 1 terabyte hard disk, you see in the material, some in the inside material, phosphorus and whatever. This orange one is rutetium, and this is a little bit of witchcraft. But why I'm showing you that you see a lot of different elements have any to do. And I'm absolutely no expert of hard disks, so I have no idea how they work. But what you see at the beginning, this small purple peak, which is carbon, and that is in the range of, and now it comes into detail, these are not micrometer, these are nanometer on the scale. It means this is 0.7 nanometer, 0.7, 0.68, 0.76. Means our resolution of the system is below 1 nanometer, the depth resolution. And that is fair enough for nearly all technological processes.
Yeah, I remember when I was a bit younger, I was working with a standard Spark OES, the old-fashioned one before it was digitalized, and we only had sensor cells for the standard component we have in steel. So if we needed something else, you needed to add that. Do you have, as a standard, all the elements mounted in the glow discharge machine?
Well, the LECO machine has CCD detectors, so we cover the full wavelengths from 120 to 850 with nanometer.
Yeah.
So we always see the whole spectrum. Of course, we're not using the whole spectrum. We're using just some wavelengths where we have that we use in the calibration, of course, in the system. But theoretically, all elements are always there. It's more really a question of calibration, finding standard materials. There are not standard materials for everywhere, for everything. But this is true for all.
Yes.
Spectrometers. This is the same with the Spark spectrometer. If you have a standard material, we can calibrate it. If not, we have to see what we can do.
Yeah, because I also remember I had the iron base, but I was not able to measure with any kind of accuracy aluminium or copper or other alloying systems. But how does that look today?
Well, I would say if you come to normal technology alloys, there's enough standard material for answering all questions. It might be different if you go to some exotic stuff or go into research sites. We can measure always with our machine everything. The problem is you have to calibrate it anyhow. And if there's material available, the customer can easily calibrate that if he has material with a known concentration. Again, for typical samples you use in industry, steel, copper, aluminum, this is all there. If it comes to exotic stuff where anybody doing high entropy alloys or whatever, of course, then we have to see how to calibrate it. But generally, in most cases, there's an easy solution for that.
Yeah. It looks very easy compared to what I came from.
Yeah, what is, come on, this is a philosophical question. What is easy? What is the easy? No, it is used in routine application. You even can find systems on the internet where they're using some automatization systems. That's there.
Fantastic. I really like the glow discharge and the accuracy to be able to dig less than 1 nanometer per sample and then just take it layer by layer by layer. Is there a limit how deep you could go? Can you go deeper than 100 micrometer if you wish?
The problem is if you go deeper and deeper and deeper, you will anyway reach the point where your plasma goes down, where you're losing your plasma. And if the plasma is lost, the sputtering process stops and no light. But 100 microns is always. I saw also examples of 150 microns and so on. Though but it will not be 5 centimeters. That definitely not.
Yeah. Michael, I have the last maybe dirty question. If you can measure everything with this glow discharge, why should I use the sulfur, carbon, or the oxygen, nitrogen, hydrogen machine?
Oh, simple answer. I need a solid sample. As soon as a sample is a powder or chips or drillings or whatever, then we can't do that with GDR, with any spectrometer, by the way.
Okay, yeah. So if it's a melt shop and you can make a lollipop and you have a dense surface bigger than 4 millimeter, then
yes,
you could use this with the same accuracy.
This is now really that's a difficult question. No, not with the same accuracy. Because the oxygen, nitrogen, hydrogen analyzer, of course, if you take into account the amount of material it's used, it's 1 gram. We will not sputter 1 gram. You can calculate that 4 millimeter and 50 millimeters microns deep. This is some micrograms. So that will be always a different thing. Also, the sensitivity. I mean, we can measure sulfur with our machines. I didn't show that example. In the below 1 ppm sulfur range, or hydrogen in the range of 0.0 something ppm. There are of course differences.
Yeah, but in the glow discharge, when you are so accurately, you could also be able to measure if you have segregation in grain boundaries. So does the chemical composition of an alloy system change on the way down?
Yes, of course it does. But I mean, you have to see if you make just a surface measurement, or if you make a measurement. How should I explain it? If you have a sort of steel bar and you make a cut through, and you take what you get and measure it from point to point like this. But this can be done with any spectrometer. You will definitely see in some cases that in the middle of the bar, some elements have different concentrations than on the outer rim.
Yeah.
This is the art how to creating a static upsample, by the way, where this should not happen. But on a really technology sample, that could happen, of course. That's a well-known behavior of all metallurgical processes.
Yeah. I remember I was measuring some extremely special alloys, tool steel with high amount of vanadium, and when measuring that on a standard Spark OES, I did get different results as a function of the carbide size. So in the core of the product I made, I had coarser carbide than I did at the surface. But the chemical composition should be the same, but the measurement could vary. Instead of 9%, it was 8.5 or a 9.2. So I had quite a big variation.
Well, it's difficult to say anything to that. One thing, generally, the GDS spectrometer, due to the non-thermal removal of the sample, it's just more or less mechanically hit out by the accelerated atoms. The metallurgical background of the sample is not really the most important thing. Of course, if you have an unequal distribution, that you have a 10 centimeter sample, or let's say 5 centimeter sample, and in the middle you have 5% more manganese than in the outside, you will never get a good result. No. But generally, we are not really sensitive, or not really influenced by the metallurgical history of your sample. For example, we also can analyze, just as an example, gray cast iron in a very good way. Yeah. So it must not be white cast iron. We can really use it as it is, because we have a non-thermal plasma. It stays more or less cold, gets a little bit warm, but it's not glowing hot. So we have no influence with that.
Fantastic. Michael, my last question is, if people want to learn more, what could they do? Are there conferences? Are there papers? Are there special classes they should participate in?
Yes, there are quite a lot of papers. Not only LECO. This is no advertisement for LECO. This is there are a lot of papers available on GDS since the last 30 years. There are some conferences. There are some user meetings. There's a European work group for GDS. There are some addresses. So if anybody needs an address, maybe the easiest way is that you forward him to us, and we can send him or her suitable addresses or links, or URLs to go deeper in the system.
Yeah, or we can put the link in the comments on the YouTube channel.
We can do that.
Perfect. Thank you. Peter, I really enjoyed it, and I learned a lot today.
Hopefully. And I have to say thank you for the possibility, and it was nearly 1 hour, so thank you very much for that, and greetings to Sweden. And bye-bye.
Yeah, see you. Bye. Thank you for watching. I really hope that you enjoyed the story about how to measure the chemical content of an alloy in a speedy manner. If you like it, feel free to share it. I would love your comments. If you have ideas for new episodes, or if you have questions, please post them in the comments below here. And hang on, subscribe to the channel, because the next episode I will go fundamental on the purpose of this channel. The name is Everyday Metallurgy, and what is more everyday than looking into the coating you have on nails, bolts, and screws. And I have been so lucky to get an expert from South Africa on board, his owner of a shop that makes these kind of coatings. So hang on, subscribe, and wait for the next episode. It will be great. See you.